So it's week 4, it's Wednesday. We've been studying recursive backtracking, and we're going to keep doing that more today. That's basically the topic for this whole week. That's the topic of your 4th homework assignment that goes out at the end of the week. So yeah, that's what we're going to do. I just want to do more practice. I think the more examples you see, the more it will make sense. I encourage you to practice on your own, as always, and also in section. The next few days you'll get more practice as well. So I want to go back to the problem that we were working on last time. We were trying to print out all of the dice rolls that led to a certain sum. Remember this? We ended class with this. And we actually finished it. We got it to work. I'll show you the code that we wrote. This is the code. Now, a couple of things just to remind you some of the concepts that come up when you do recursive backtracking. We decided that we wanted to write a helper function because we needed a way to keep track of the choices that we had made along the way. This is a common trick that you use when you do recursive backtracking because each call makes a choice. You gather together a series of choices and then you do something with them, and so you need to keep track of the choices that were made along the way. In this particular problem, those choices are kept track of in a vector. We call it vector chosen. So this works. I mean, if you run this, the main function asks for the dice sum of 3 to 7. 3 dice rolling to make 7 for the total sum. It prints all of those combinations. It's totally correct. But I think I said briefly at the end of last class, I didn't really think this was a great solution overall. What's not great about this solution? I don't know how to turn Slack off, so you're just going to see my chat messages during class. Hopefully nothing too racy in there. Anyway, what's not so great about this solution? What do you think? What could be better about it? Yes?
It checks every possibility, even though that might not be the sum. It might not be the sum of that.
It checks every single possibility, even though some of those possibilities might not lead to a good outcome. Right. So if you want that to be made more concrete, let me try to help with that. I'm going to do something that I don't want you to do. I'm going to show you something a little bad, a little dirty. But, you guys are grown up enough, I think you can handle this. I'm going to show you something called a global variable. Now, global variable is when you declare a variable outside of all of your functions. Now, we don't usually do that because it's important to restrain the scope of data in our program to avoid bugs, to have better separation. But just for a brief moment, I'm going to do that because I want to use it for a particular purpose. I want to count the number of times that our function gets called. Okay? So down here, every time we call this helper that we wrote, I'm going to say calls plus plus. That's all. And then up in main, I'm going to see how many calls it took. See out total calls colon calls. Okay? That's all. Let's run it. And it takes 259 calls. Well, okay, I don't know. I don't know if that's good or bad. I don't know. Let's try 4 dice to get a sum of 11. Let's see how that turns out. Makes 1,555 calls. That's kind of a lot of calls. Function calls have overhead. They incur performance penalty, have too many function calls. And I think what you said was that some of these function calls might not be necessary. So I don't know if it's obvious just from looking at this, but I tried to draw this picture of our, oops, what did I just do? Sorry, I clicked the wrong thing. Where is it? What happened? I lost something here. Undo? There it is. Somehow I threw away that slide. Our code is doing something vaguely like this. Let's say we're computing dice sum of 3, trying to get 3 dice to add up to 5. Well, the first die could be any value from 1 through 6, right? And we try them all. But it's kind of dumb to try them all, right? Why try 6? If you're trying to add 3 dice to get a total of 5, why pick the first one being 6 and then explore a bunch of stuff that could happen after that? None of that stuff's going to work. We know that, right? Just by the numbers. In fact, you make a stronger statement than that. If I want to roll 3 dice, what's the biggest value the first die should even try? 3, actually, because the remaining dice have to be at least 1 also, right? So if the first die is even 4 or 5, then the remaining 2 dice at a minimum would be 1, and you get up to at least 6 or 7, something like that. So this is wasteful. It's wasting a lot of calls, okay? So all I want to do is I want to try to make a small optimization to our program so that we don't make calls if it's just really obvious that it won't work out. If you look at this code here in the dice sum method that we wrote, the function that we wrote, do you have any thoughts about like how we could tell if it was worthwhile to make calls or not? I mean, another way of saying it would be like, maybe if we ever get into a state where we know that it's not going to work out from here on, maybe we would immediately back up and stop. That's another way of thinking of it. How would I check that or incorporate that idea into this code? I can help you a little bit. How about this? If something, then I will try all of this work. But the something sort of means, is it possible that what I've done so far could lead to a good outcome? Okay, so for example, if I pick the first die of 6 and I want a total of 5, that would not lead to a good outcome, right? Any thoughts? Yeah?
The number of dice we have left to roll should be less than the desired sum which we're trying to get.
Okay, so I think the great way to say it is kind of what you just said, rephrase is like each die that's remaining to be rolled can be at the minimum a 1 and at maximum a 6. So that the space of sums we can reach from here is that, right? So why don't we just check if we are within that close to our desired sum, basically, right? So the desired sum, like what's the minimum desired sum? The desired sum has to be at least the number of dice I have left times 1, right? You understand? Like, the least I could do is get 1 for each die, and the desired sum has to be at most the remaining dice times 6. Does that make sense? That'll also cut stuff like negative, like if we overshoot it or something like that, right? If we do that, it still prints all the answers, but instead of printing 1,500 calls, it makes 847 calls. It cut a lot of calls out of there. I think the down here, if I do 3, 7, or whatever it was, 3, 7, that one printed like 200 and something. Now it cuts it all the way down to 127. And actually, a lot of those calls that are made, a lot of those 127 are really fast calls where it just really quickly, bails out or something like that. Really avoiding all these unnecessary loops is an even better optimization. So look, I just wanted to show you this. Sometimes when you have backtracking, there's such a big space to explore that if you start going down a path that's bad, you need to recognize it and you need to withdraw and try a different path right away. Because otherwise you'll just be searching and searching and searching and searching. This problem isn't super tuned for illustrating that because the dice search space isn't that big, but the more, if you were rolling 12 dice, then this would really, really matter. You know what I mean? Because it's exponential amounts of growth that we're talking about here. Anyway, that's sometimes called pruning the call tree, trimming the call tree, trimming branches off of this picture basically here. Okay? So that's all I wanted to say to finish that example from last time. So now I would like to move, that was from the slides from last lecture. I want to open the slides from the current lecture, from the Wednesday lecture. So let me do that right now. And let's just look at some more problems. Remember the overall strategy before we start to write another one from scratch. The overall strategy for backtracking is, if there are choices, then you're going to handle one of them. So for each thing you could pick for your part, you choose it, you explore what could follow, and then you unchoose it. Choose, explore, unchoose for each possibility. Bless you. And if there's no choices left to make, you either stop or you print the choices that you found or whatever. So, in any backtracking problem, we're trying to figure out what work is done by each call. How do I slice this work up? And how do I enumerate or try all the things I could handle for each call? Yes, question?
Do you only choose when the output is on the side?
Oh, good question. Yeah, do you unchoose always, or do you only unchoose when you've reached a bad point? You unchoose in both cases, but I guess the sort of undoing because I don't like where I have reached. You could undo for two reasons. One's because you have made all the choices and now you're done and now you want to print what you've chosen or something like that. Or you could undo because you know that you aren't going to reach a good outcome. So once you have definitive answer, either way, you need to backtrack out. So I think most of the time the code kind of has these three steps: choose, explore, unchoose, in sequence. So I think we'll see that through the examples that we write together. Okay, let's look at one. I think this one clicks for a lot of people. I like this one. Let's do this one together. It's escaping from a maze. This is like literally backtracking. So what I want here is, I'm going to give you a little maze with walls, and you can walk through the corridors, but you can't walk through the walls because we're mortal humans and all that. So you're going to be at a certain location, a certain row and column of this two-dimensional maze, and I want you to see if you can find a path to get out of the maze. And I want you to do it using recursive backtracking. And I mean, you might have heard of different tricks for how to get out of a maze. Some people hold the wall with their right hand or something like that. But I want to do it with recursion. I want to do it with backtracking. And basically what I want to do here is I just want to try all the different ways that you can go and see if any of them lead to an exit. That's the idea. And if you try a certain way and it doesn't lead to an exit, what do you think you do? You cry. You start sobbing in the corner to yourself. Then what? You go down a corridor and it's a dead end. You backtrack, you unchoose, yeah. Then you are eaten by a grue. Never mind, no one plays Zork anymore. So this is very literally a backtracking idea. Now you might say, well, wait, how does this maze work? Is it a grid? What is it? I want to kind of avoid some of the muck and the details here of the computation, so I'm going to help a little. I'm going to give you a class called maze. That basically is like a grid. You can ask, how big is the grid? How many rows and columns does it have? You can ask whether you're within the boundaries of the maze, just like you could with a grid. You can mark squares, like you're leaving breadcrumbs of the path that you're taking along the way. You can also do what's called tainting a square. Tainting means you have marked it as being a bad square that you don't like. You don't want to go that way anymore. So there's these different methods that we can call. This is basically just a kind of a wrapper around a grid so that we can express some of these ideas in a simple function call. Okay? So let me show you the file that we're going to work on here. Oh, where'd my project go? Man, I'm having some computer stuff today. I don't know. It's not my day on the computer. So I've got a file here. So first the thing I need to do is I need to go to that dice rolling. I need to turn the main function off by renaming it. And then in the maze, I got a main down here that I need to turn on. And there. Now we're going to write this. Escape from the maze. Okay. Oh, I think did I put the right slide up on the screen here? There. So I want to mark a pathway out of the maze if there is one. And I also want to return a Boolean value indicating true or false whether there is such a path, whether I found a path out. Okay? So from any given square, you can move to a neighbor. What's the general algorithm here? It's recursion. What are some of the things we usually think about when we write recursive code? Yeah, okay. That's one of them. What's a base case for this? What's an easy thing to answer whether you can escape or not? Yeah? If you have already escaped, then yes, I know I can because I have, right? So yeah, you know you have escaped if you've gone out of the bounds of the base. So how about base case if we are out of bounds, in bounds? If we're not in bounds at this row and column, then hooray, we escaped, return true. Okay, fine. Are there any other locations that I could ask you about where you could definitively say, no, starting from here, it is not possible to escape the maze, and why? Are there any other base cases? That's basically what I'm trying to ask you. Some recursive functions have multiple base cases. Yeah?
When you have a wall on 3 sides.
If I'm surrounded by walls? Yeah. And actually, I think there's an even simpler way than that. What if you're just like in a wall? What if you say, can I escape the maze starting from here? You'd say no, because you'd be dead. You'd be inside a wall like Han Solo or something, right? You can't start there. You can't even be there. So, and I think that kind of subsumes your case. I think, because what you might say is if I'm surrounded by walls or whatever, I could sort of ask around me, can I escape from those places? And if they're all walls, then they would all say no, false. So then I would sort of also know that I can't escape from me either. Do you know what I mean? So there's going to be that kind of idea of like, what's going on around me? So I think what we can say here is if the maze has a wall at this row or column, that's also a case where no, return false. Okay? Else, so now we're starting to get to the point where maybe we need to write the sort of main algorithm. So it might be hard to see the self-similarity here, but like if you're just standing at some random place like this, what do you think you could do? I mean, remember what recursion is, right? It's hard to find a path out of a maze. But we're so lucky that we're writing this recursively, we don't have to find a pathway out of the maze. We just have to do a little bit of work. We just have to make a little bit of progress. And if we do that, and if the magic of recursion does the rest, then maybe we'll get a way out of the maze after all that. You know, it's magic, right? So if I'm standing here, what could I do in my call that's a little bit of work to help me try to find a way out of the maze? What do you think? Try going up one direction, go one step to the left and look around and yeah, just move a little. Yeah, I think that's a good idea. Okay, so there's not really like a move method, but there is kind of a recursive function that we are writing, which is like, can you escape the maze from a given square? So how do I take this idea of like move one step? How do I express that in this situation? What do you think? Okay, so like maybe mark where I'm standing. Maze.mark where I am. I've been here. And now what? So remember that recursive backtracking is about like, let me think of all the things I could do. I'll make one small choice, but I'll try all the different options I could make for that choice, right? So if I'm standing, I think I said right here, well, what options do I have? I could go this way or I could go down. Like I could go those different ways, right? I could even try going these two ways, but I think right away I would find, nope, that's no good. I got to back up, right? So why don't I sort of try going all four directions and see if any of those work out? Why don't I just say escape maze, maze. So going up is row minus 1 and the same column, that's up. Going down is row plus 1, down. Going left is row col minus 1, that's left. And go right. So that's kind of the idea. We're not quite there yet. Remember that you have to return a Boolean value that indicates true or false. Did you find a path out? So I need to return something here. How do I know what to return? What do you say? Yeah.
So, if any one of those four calls returns true, then you know you can escape the maze. So you can just turn like escape maze, or and then have an or between those four calls.
Yeah, that's a really great insight. Thank you. I'll repeat that. You said those recursive calls all return Boolean values. So you guys are probably thinking of these calls as like, you know, computations or steps I'm taking or whatever, and they are that. But they are also questions that have an answer that comes back. When you call escape maze on the up, you're also asking that call, hey, did you find a way out? True or false? And if it brings back a true, what you should know is, oh, if I go that way, there's an exit that way. Right? So if there's an exit that way from me, I can just go there and then I'll go to whatever exit that is. So if he can get out, I can get out. You know what I mean? If my neighbor can get out and I can just walk to my neighbor, then so can I. So same thing. But if I try to go up and that returns a false value, then it didn't work. There was no way to find a way out from up. So that doesn't work, so then I'll try the next one, and then I'll try the next one. So, I mean, one way of thinking of this is you should really say, if I try to escape the maze up and it returns a true, then I should return a true. You know what I mean? I should try all four. I could do if return true, if return true, if return true, I should try all four, and that's what I should return. Now, you gave me a more elegant version of that same idea, which is what you said, just call them all with an or between them, because if any of them works, then I work. So I think that's a great way to phrase this. So I will do that. You said return whether I can escape maze going up or I can escape maze going down. I'll take out this equals true. Or I can escape maze going left, or I can escape maze going right. Return whether or not I can get out by doing one of those things. Now you might say, wait, does that mean it does all of them? No, actually the way that C++ executes the code is it does the first one and waits, and only if the first one is false does it go on to the second one because of a process called short circuit evaluation. So this is the basic idea of this algorithm. I think I can run it here. We might not be quite done. Oh, you have a question? Oh, did I mess up my indexes? Let me see. Oh, yeah, you're totally right. -1 for left, plus, thank you. There's nothing better than having like 400 compilers watching you while you code. I love it. I appreciate it. Thank you. Yeah, that might have been nasty because it wouldn't have given me a compiler error. It just kind of wouldn't have always found the exit, and I would have been like, oh man, how come it's not working? So yeah, load. I'm going to load up a file here. And so if you just click somewhere, it's supposed to try all the different ways. Here we go. Oops. What happened? Let's see, what happened here? Is not an unmarked open square. Oh, okay, so like this thing gets mad if you try to mark a square that's already marked. So, I mean, I think most of what we have here is good, but like it's just a little mad at us because we're trying to double mark a square. But let me ask that question. If we're crashing because we're trying to double mark a square, what does that mean? Just conceptually about our algorithm, what does it mean? We went in a loop and got back where we started, right? We kind of don't want to re-explore stuff we already explored. If we go in a circle, it's like Hansel and Gretel and the breadcrumbs or whatever. If you get back to the breadcrumbs again, you know that you're going the wrong way or whatever. So you probably want to do something like if this square isn't marked, right? And actually, I think there's a method called isOpen, which is a good one. If this square is open, that means it's good. I can go here. So let's try again. Okay, so now actually I'm getting an error now because it says not every path through my code is returning a value. This is a pretty common error, which is when you have if, else, if, else, if, else, if, and you don't have an ending else to say what if none of those cases succeeds. If I get all the way down here, then I think what happens is I'm on a square that isn't open. I've returned to a previous square I've already been to before, so I think I should say return false, something like that, right? So let's try again. Okay, let's do this. Maze 1, and I'm going to click right here. It's kind of cool, huh? It's pretty much working, pretty much done. The only thing I would change about this is I think if you go down a dead end and it doesn't work and you back up, I'd rather kind of cut those squares out and say those aren't part of the path. I only want to mark the squares that are actually part of the path we end up following. So for example, like this square, these two, these ones, we're not actually traveling those. That's not part of the path we really want to walk. How could there's a thing called tainting a square, which is like, no, this one was bad. I don't actually want to go here. Where might I do that? What do you think? Also, related question. This is really asking about the same issue. Remember how I said choose, explore, unchoose? That's usually the model, right? Well, where is that in this code? Where is choosing and where is exploring and where is unchoosing? Where's choosing? What's choosing? What's that? When we say mark, when you mark a square, I choose, I'm going to go here. I'm going to walk here. Yes, totally. Choose is this, right? Where's the exploring? That's the return statement with all the recursive calls. The recursive calls are always the exploring part, okay? Good. Where's the unchoosing? Nowhere. We don't really have that, right? So I think the unchoosing here would be like, if I try to go all four directions and none of them work, then what I can conclude is that this square isn't any good. I don't like to be here. None of my neighbors worked out for me. This square is not going to be part of a good path or a solution. So I think the unchoose would need to come here. But just because of the nature of C++, if you say return, there can't be any code after a return. So maybe what I'll do is I'll say bool result equals this. And then if I have to unchoose, I'll do that. But then I'll say return result. You know what I mean? So it's like if I want to do something before I return, I can. How would I unchoose? Well, I could say the opposite of what I said when I was choosing. I could say unmark, but I think in terms of the problem spec, there's an even better thing to say, which is to say, I want to taint this square. I cast dispersions upon thee. I hate you, square. Never come back ever again. So whatever. Yeah, so if I click here, what happens? Do you see when it backtracks, it grays out? That's the tainting part, right? It's backtracking. So, uh-oh. Oh, no! Thought we had it there, didn't we? Freaking recursion. Gets you every time. What happened? How do I fix that? Small fix. Yeah?
We don't want to take the square like if it didn't work out.
Only taint the square if it's bad square, if the result was false. If there's not a good result here, then taint, yeah. There we go. Let's try again. Okay, I'm excited. I think it might actually work this time, you guys. Ready? Here goes. Oh, wait for it. Kind of cool, right? I mean, I couldn't give you a more visual depiction of backtracking than this. It's literally backtracking, right? So, and I mean, I could open up other mazes. I think it's going to work for the general case, but it tries as many paths as it needs to try until it finds one that works. There is the issue of if there is no path, what will happen? I think it'll just try a bunch of stuff. It'll end up tainting all the reachable squares, and then it'll give up. But that's okay. That's probably what it should do. So any other questions about this algorithm before I want to do another problem with you guys too, but does this kind of make sense, what we did here? Do you see the recursion and the backtracking going on? Yeah.
Can you just put the maze don't have this for like everything that
I'm sorry, can you say it again, please?
Can you put the maze don't have like in the house like
Oh, the change in the else? You mean down here?
yeah, wherever it returns from.
You could rearrange the code so that would work, but I think the way the code is currently constructed, you won't get to the else if you go in the middle branch there. So I think what you have to do is delete this as an else and put the stuff down under the nested ifs and else's if you wanted that to work. Yeah, there's different ways you could express this, but basically this is one of the ones that will work. Any other questions about the Maze Explorer? This, by the way, if this example was a little confusing, it's also in the book. I think it's in chapter 8, maybe 9. I think it's in 8. You can read it through. In the book version of this, they actually enumerate the 4 directions using a for loop because they just sort of declare them all. They declare all the indexes they want to go to, and then they loop over that. You can write the same thing using a loop if you want, but it's still recursive and backtracking. Yeah?
And so when they enumerate it, so like the north, south, east, west, like the row plus 1 times 9. So if we were to do that here, we would just put in there like north, south, east, west.
So, I mean, one of the things we're going to see, I think this will also come up with the next problem. Some backtracking problems, you use loops. Some, you don't. And how do you know? Well, it depends. I mean, what you want to do is you want to think of what are all my choices, what are my options. So in this problem, I go, oh, it's up, it's down, and left, and right. Those are my options. And then the next question is, well, how do I write that in C++ in the most clean way? If there's like 35 different options and I have them in a vector, why don't I just loop over the vector and recur on each one? But if there's like 4 and they're kind of different enough that it's hard to combine them in any way, then just write the 4 things out. You know, like I think we did this with print binary where it's like, look, it's either going to be a 0 or a 1. So just like call it with a 0 and then call it with a 1. We don't use a loop. But when we're printing decimal numbers, base 10, there's 10 choices. It's pretty redundant to write out 10 calls. Do a loop from 0 to 9. So yeah, that's. Well, I think you'll see that also in this next example. Okay, let me turn this main method off so I can do the next one. The next problem I want to do with you guys is I want to talk about permutations. I think this is an interesting problem. You're given a collection, a vector of strings in this case, and I want to print out all of the rearrangements of that vector, ordering of the elements of that vector, all the permutations of it. Vector of strings. So if the vector contains A, B, C, D, you'll print out all of these. I wrote out all the permutations for you. Okay? Now, the first time I ever saw this problem, I thought, wait, isn't this just, why do you need recursion or backtracking for this? Why don't you just use like a for loop or something where you swap things and print and go write it. I think what you'll find is it doesn't really work that well. I mean, it seems like maybe you could do this with a loop or a couple of loops or something, but I think what you'll find is it doesn't solve as cleanly that way as you think it would. So I want to do this recursively. I want to do this with backtracking. How is this recursive? How is this self-similar? Where's the similarity between permuting something and permuting some other thing? What do you think? When you look at this output, do you see any self-similarity here? Any ideas? Yes? Yeah, you're right on there. You said, if I pick the first element to be A, really I want to print that followed by all of the permutations of all the other three elements, right? Permuting 4 elements is picking one and permuting the other 3. That's exactly the self-similarity. Great, I love it. So I just think that the core of the problem here is we need to turn that idea into working C++ code. What is a good base case? What's a vector that's easy to permute? Empty, no elements. So yeah, at some point we're going to run out of elements, so maybe that's kind of the way that this works. Okay, so when you write a backtracking algorithm, you usually make a helper function and you usually pass extra parameters to help you. Usually the reason for those extra parameters is to keep track of the choices that you've been making. We didn't actually have to do that with the maze explorer. Did you notice that? When we did the maze, we didn't write a helper called explore escape maze helper. Why not? Why don't we need any extra parameters? Where are we remembering the choices that we're making in this problem? That maze object is storing that for us. And because of that, we don't need to make some other structure to remember that for us. That's just an aspect of this particular problem. Okay, so let's do permute. I've got a vector that stores MART and Y, and I want to permute it. I just said a second ago, we usually want to make a helper. So let's make a permute helper that still takes a vector of strings called V, but we will also pass in a way to keep track of what we have chosen. How do you think we should keep track of what we've chosen? We could pass a string. The output we're supposed to print looks like a collection, though. So I think it might be easier to pass a collection of what we've chosen, a vector of the elements we have picked so far. So I would say a vector of strings called chosen. So in the main permute function that we actually have to write, we'll make a vector of strings called chosen, and we will pass it to permute. You know, we always have to call the helper to get the whole thing going, you know. So we'll pass v and chosen. So initially we've chosen nothing, so the chosen vector is empty. That's how the recursion begins. Okay. You told me that what I need to do is pick an element and then follow it by permuting the rest of the elements, right? How do I pick an element? Which element should I pick? Like, imagine I'm the first call. I'm the first one. No choices have been made. I've got A, B, C, and D. I could choose any one of them. Which one should I choose? A? Well, I mean, is that the end of it then? I choose A and that's all? I mean, I guess maybe it's not clear what I'm asking. Like, I should choose all of them, one at a time. I should choose A and then try that. I should choose B and then try that. I should choose C and then try that. There's no bad outcomes. It's not where I'm going to get to a bad state and withdraw from it or whatever, but I need to do all of them. I need to try all of them as being first, and then I need to try all of them as being second. So the idea here is for each choice, choose, explore, unchoose, right? So for each choice means for each element of the vector, so for each int I going from 0 to v.size, right? So we are going to be using a loop here. For each of those elements, choose it, explore it, unchoose it. How do I choose something? What does that mean in this problem? Yeah?
Yeah, it's a chosen vector.
Put it into the chosen vector. That's the place where we're storing the things that we have chosen, so that sounds great. Okay, chosen.add v bracket I. We're going to try element I being first, or being next, or whatever, right? Okay, is there anything else I need to do? Yes, but what is it? That is part of choosing. If I'm the first call and I pick A, what else do I need to do to indicate that choice, aside from putting it in the vector? Somebody I haven't called on yet, maybe. I've been ignoring y'all on the top. I'm sorry about that. If any of you up there waves at me, I'll try to call you. I see you. I'm sorry. I don't remember. You can play next time. I'll call you. See, now I'm looking at you and you're not raising your hand this time, are you? You're like, no, call me when the answer is base case. I know that one. I know base case. It's okay. What else do I need to do to remember my choice? Oh, yes. Go ahead. Remove it out of the vector v, because I can't let the next calls also choose it, because I've taken it for myself. So pull it out of the set of choices. That's exactly right. v.remove the element at index I. Pull it out. Okay? So if you want to, I don't know if it's hard to picture what's going on here, but like imagine that the chosen vector is initially empty and I'm looking at a vector of A, B, C, D, right? Well, if I choose element 0, which is A, then I want to set the vector v to be B, C, D. You know what I mean? So for the next call, they don't have A in there again. That's what you said. So, okay, explore. Explore is usually the recursion part. So I'll just say permute helper, and I'll pass v and chosen. I'm passing the same parameters, except I have changed their state. So now it's sort of different for the next guy, right? The next guy gets an A in the chosen vector and a BCD in the v vector. And presumably they will make further choices that further change the vectors and so on. Unchoose, I think some students get a little mixed up what happens here. Keep in mind that permute helper is going to lead to a tree of things. You know, if I'm the first call and I make another call, that's going to lead to lots and lots of calls under that. Eventually all those subcalls are going to come back. And what that means is I have now finished processing or printing everything that could possibly have started with the letter A or the element I or whatever. So once I'm done, I need to unchoose the letter A and then advance and try the letter B or try the letter C or whichever one is next. How do I unchoose? Here. Give your hand up? Yeah, go ahead.
Just clear the chosen vector.
Okay, so pull that out of the chosen vector. You said chosen.clear. I don't think that's perfectly right, because you have to picture that this same code is going to run on the first call and the second call and the third call and the fourth call, and the fourth guy shouldn't clear the choices that the second or third guy made, but they should undo the choice that they made, right? So like, how would I do that? Remove the last element. Now you have to be careful. If you say I, that removes the element at index I. So I think what you really want to say is I'm the last one who added to the chosen vector. So I want to remove, I think it's called remove back or remove last, like remove the last element from the vector. That's the one that I put in at the end of the vector in the first place. There's one more line I need to do. Basically, it's the opposite of these two lines is what I need to do, right? Often, unchoose is pretty much the mirror code of choose. So I have to remove from here, and I need to add to here, right? And so how do I put it back in V? I could say v.add whatever, but I actually don't have the value anymore. So maybe what I'll do is I'll say string s equals that. So I'll save aside the string that I'm choosing. And now I will, down here, I'll put s back into v, except that's not quite right, because the way I removed from v was that I said delete the person at index I, so I should put them back in at index I. I have to mirror these things as closely as I can, you know what I mean? So really what I should say is insert at index I, put the value s back in where I took him out of before, okay? Do you see the pattern here? I think it's a little hard to read at first, but this is the idea. Pick an element, choose it, explore what can happen next, come back and take it back out, unchoose it. Yes, go ahead.
Could it work if you like inserted it before you remove back? Would you still need to do the string?
Oh, you mean grab it out of here and use that to insert, and then I don't need the string s? Yeah, I think that would be totally fine. That would totally work. There's always more than one way to do it. I don't think there's anything bad about having a variable. It's fine with me. So either of those ideas would be fine. There is something missing here. Anybody in the back want to tell me what I'm missing in this code right now? What's missing? The base case. Thank you. I'm so happy that you are here. It's missing the base case. And that's actually the right answer here. There's no base case, right? There's no base case. What is the base case? I know we kind of said like empty or nothing, or when you're, empty vector or that kind of thing, but remember when we have backtracking, the base case usually follows a set of prior calls. So I wouldn't think of it as an empty vector necessarily, like I'm asking you to permute an empty vector. It's more like I asked you to permute a big vector and it got whittled down until it's just nothing. That's when we reach the base case. How do I know that? How do I know that I got to that base case? What is going to be true at that point? Somebody raise your hand. I have too many whispers. I can't really see. Somebody had a call on. You want to tell me? Got it?
The chosen will be full.
The chosen vector is full and the v vector is empty. That's how you know you're done choosing stuff. I think it's probably easiest to just check the v being empty. The chosen being full is fine too, except that I don't always know how many elements constitutes full. So I'll just look for the v being empty as the easier. Those are equivalent ideas though. So if v is empty, that's the base case. That means I've already finished making all the choices that I need to make. Otherwise, I'm going to do all this stuff, okay? If v is empty, I think the point of this problem is I'm supposed to print out all these different permutations. So I'll do C out what I have chosen, followed by an endl. Could this possibly work? No, it doesn't have a main method. But that's because I renamed it. That's not our fault. Let's try again. Wow. I think it worked. Marty, Marit, Matri, Matter, my rat is in here somewhere. My rat. My name has a lot of like dirty anagrams of it, actually. My full name, I'm not going to tell you what they are. But yeah, you might learn that later. But I think it's working. If you're like, okay, I don't see why it works, it doesn't really make sense to me. I keep coming back to this way. I think my favorite way, if I have the code in front of me, if I'm in Qt Creator, my favorite way to understand what the heck is going on is to put a print statement at the start of the function call. So what if I just do cout permute v equals v, chosen equals chosen, and endl. And I think, didn't I do that recursion indent thing where it indents the calls? Let's do that. I have to include this thing called recursion.h. And then if you do that, you can say recursion indent followed by that stuff. So watch this. Oh, actually, it's actually out of output. So wait, let me hold on a sec. Let's go a little shorter here. Let's go A, B, and C. Okay, that's easier to read. So try again. So look what happens. We call it with v full of stuff and chosen is empty. So that leads to 3 calls. It leads to this call, and it leads to this call, and it leads to this call. It leads to me trying A first, and it leads to me trying B first, and it leads to me trying C first. And then after that, we explore all the stuff that could have A first. We explore all the stuff that could have B first. We explore all the stuff that could have C first. And so the second call is this guy. You've already chosen A. Oh, wait, where am I? I'm on the wrong line. This guy right here. You've already chosen A. I've got B and C to choose from. What will I do? Well, I'll try 2 things. I'll try choosing B, and I'll try choosing C. And so each one leads to another call afterward. Eventually you get to the point where there's nothing to choose, you print it out. So that's kind of the tree of all the calls here. Permutations. What do you think, guys? You have questions about this one? Does it sort of make sense? Yeah.
Where do you see the unchoosing?
Can you say it again?
Where can you see the unchoosing there?
Where can you see the unchoosing? I don't have any printouts that show that. What I could do, I don't know if I have time to. I think I might omit it, but the unchoosing would be like I could put a print here. Okay, sure. Let's do it. Here. I think I was trying to decide, like, what am I going to do with my 5 minutes that I got left? And I think what I want to do is just, like, really understand this as much as I can during that time, you know? So how about here? This is right after I chose something. So what I'm going to do is I'm going to say, I choose S, right? And then why don't I print V now equals V, and then I'll say chosen now equals chosen. Okay, so just more printing. You should do this. Like, it's hard to understand this stuff. Go download it, print it, do all this stuff. So now down here, when I'm unchoosing, I'll say I unchoose S, and I'll print V, and I'll print chosen. Cool? Okay, let's see if that looks good. So this should look similar to before, but with more stuff. Okay, what do I see? Permute. Nothing's been chosen. I choose A. Later it's going to say, it's a little hard to read this, isn't it? I unchoose A. Way down there. Oh, no, not this again. So I choose A. So now let's do that. Now the second call is made. So A has been chosen. They choose B. Later on, they unchoose B, and they choose C. So I don't know. I don't know. It's kind of hard to read with all that extra output, but think messages like that, printouts like that, would be a way for you to trace through the code in even more detail. And I totally encourage you to do that. I think it's a really good way to build an intuition about what the heck is going on with this kind of code. Okay. I have a quick question. There's a couple of minutes left, and I don't want to start a new exercise or whatever with you guys. It's not enough time. But let me ask you a slight variation of this. What if what if there were duplicates in here and it was like A, B, B, C? What if it were A, B, B, A, C, right? So I print that. I might have to turn off some of these prints because it's just too much output, but here, let me delete these real quick. There. So now I run this, and okay, it prints all the things, but if you looked through it pretty carefully, I think what you see is that some of the same lines of output get printed twice, right? Or even more than twice. Do you understand why that's happening, right? Because one of the arrangements is what was originally the first A followed by the second A, and one of the arrangements is what was originally the second A followed by the first A. Whatever, it rearranges them both ways. And then you say, well, golly, those are distinct. They're not distinct from each other from the user's perspective. I don't want to print those twice. Do you have any ideas what would be a quick fix, a patch we could make so that maybe it wouldn't do that? Any ideas? Back, yeah.
Could you make a set of vectors and add it to the set, and that way we only do it once?
Sure, there's a lot of ways we could do this, but if we've got 2 minutes, then I think what you do is every time you print, you remember that you printed. So what you do is something like this. You keep a set of vectors of strings called printed or something. Here's who you've printed. Okay, you pass another parameter because this is new information we're trying to remember. Down here, when you make the original function call, you create that set. It's empty. You pass it along. So this is going to remember everything we've printed before. And now, when I print here, when I do a printout, I add the thing that I printed to the set. Printed.add chosen. Okay, but we're missing one last piece. We're now remembering what we printed, but the whole point of remembering that was to avoid printing the same thing twice, right? How do I incorporate that so that I won't actually print the same thing 2 times? Yeah? If the printed doesn't contain chosen, then print chosen, add to chosen. I think I need to import set, up here. Set.h. Let's try it. Too few arguments. Oh, sorry. Down here, I need to pass printed to my recursive call. Let's try again. And I think if you inspect that, my eyes are bad, but I'm pretty sure we trimmed out those duplicates. So your idea was great. So I'm out of time. I'll let you go. Go to section. I'll see you Friday. We'll do some more practice. Thank you.